So today's lesson is 7-3, logarithmic functions as inverses. Basically what we're going to be talking about today is how a logarithmic function acts in comparison to an exponential function. So our objective is to write and evaluate exponential expressions and then to write and evaluate logarithmic expressions. We did exponents last time. Graph logarithmic functions. Basically, what you need to know is that the exponential function y equals b to the x is 1-to-1, and its inverse is x equals b to the y. So to express y as a function of x for the inverse, write it this way, as a logarithm. So basically what we're saying is that an exponential function equal to y and a logarithmic function, that's this one, and a logarithmic function equal to y are inverses. Okay, so let's see how it works. So our first concept is a logarithm. A logarithm of a base b is a positive number x that satisfies the following definition. So for b bigger than 0, this is important right here. B must be bigger than 0, and b is not equal to 1. Okay, so that means that little base right down there, that's what we call it a base, is got to be bigger than 0, and it can't be 1. And the way this works is that b to the y power is equal to x. The opposite of that is this logarithm right here. You read it as log base b of x. Now, b, in other words, the logarithm of y, this, the purple, y, is the exponent that you have to raise b to get x. That's how logarithms work. The answers to logarithms are exponents. So let's see some of the rules. Okay. The exponent in the expression b to the y is a logarithm in the equation log base b of x. So notice that here and here are both y. The base in base b, the bases are the same. So we have the base b here, we have the base b here. They're both the bases, the same. Okay? And in both, b can't equal 1 and b is bigger than 0. Since b is not equal to 1 and b is bigger than 0, it follows by that b to the y has to be bigger than 0. Since b to the y equals x, then x is bigger than 0. So log b is defined only for x is greater than 0. What does that mean? Whoops. I meant to lose the whole thing. What does that mean? It means that in red, right here, it must be a positive number. Okay? It's only defined for x is bigger than 0. If x is less than 0, if x is negative, the logarithm is undefined. It does not work. You cannot do it. Okay? And our last little point right here is that because they're inverse functions, the composition map a number to itself. So what does that mean? If I take b to an exponent that's a logarithm, we are back to where you start. You're back to a. And the opposite is also true. If you take a logarithm to b that has an exponent of a, you go back to a. Okay? So out of all these, this one's probably the most important. We're saying that you just can't take a negative logarithm. You cannot have x as a negative. So let's see how this works. Okay? So follow along. We have our red term right there. We have our red term right there. We have our blue term b. We have our blue term b. We have our purple term y. We have our purple term y. So let's rewrite this. Let's rewrite this expression as a logarithm. Follow the colors. So we write log base b base 10 of x equals 2. Notice that all the colors follow along. The base is still blue. The x is our red term, and the 2 is the exponent. The logarithm The way we think about this is what power of 10 do you need to raise to get 100? So the answer is 2. 10 to the second power equals 100. Answers to logarithms are exponents. So let's try the next one. So it would be log, the base stays the same, base 3 of 81 equals 4. What do you need to raise 3 to get 81? One more time. This turns into log base 6 of 36 equals 2. What do I need to raise 6 to get 36? The answer is 2. We can use exponential form to help us evaluate the logarithm. If we are trying to think about this, well, what do I raise 8 to get 32? What power do I raise 8 to get 32? Well, 8 doesn't work by its own, so we know that the answer is going to be a fraction. So our question would be, what do I raise 8 to what power equals 32? Well, if I bring 8 down to 2, 2 to the 5th equals 32. In order to get 8 down to 2, I would need a root. That's the third root. And the 5th power. Excuse me. So my answer is that log 32 equals 5 over 2. Another way to do this is to just plug it into your calculator. A calculator function, right? A calculator function that looks like this. Log with a solid base and then an open square. Means I can put any base I want in here, any number I want in here, and it will generate an answer for me. Some calculators only have this button. We'll talk about that in a few minutes and how to evaluate any logarithm regardless of the calculator function we will do next lesson. So to finish, let's try a couple of these. So log base 5 of 125. What power do you raise 5 to get to 125? This one works out nice and perfect. Log base 4 of 32 is also going to be another fraction. It's going to equal 5 over 2. Okay? We take the square root of 4 and then raise it to the 5th power. Now notice that my answer here is a fraction. Okay? So that means my exponent, only way to get a fraction is to have a negative exponent. So 64 to the 1 over 32 is going to give me negative 5 over 6. And like I said, all those can be done very simply on a calculator. So next, this is what I was mentioning before. Sometimes the log is simply written as log x with no base. This is called a common logarithm. Common logarithm is a logarithm with base 10. So both of these mean the same. Either the log has a 10, or more often than not, it has nothing there. If you see a logarithm with nothing there, it means base 10. And the next paragraph goes on to explain something called the logarithmic scale. It's when we use logarithms. This we're not going to talk about too much during class, so you can pretty much go right past that paragraph. But if you're curious, the Richter scale is one of the things that's a logarithmic scale. Also, the decibel scale is a logarithmic scale. We will talk about, however, is a logarithmic function, okay? And how it is the inverse of an exponential function. Notice in red, this is the exponential function, okay? The red line. In blue, we have the logarithmic function right there. Okay? Both are on the graph. Exponential function goes up. Logarithmic function starts down and goes sideways. In both cases, note that our points are opposite. So this red function has 0.110. whereas the blue function has 0.101. They're opposite. The blue function has 1, 0. The red function has 0, 1. Okay? They are opposite of each other. Also note that this line right here, y equals x, acts like a mirror. Each function is the logarithmic function is a reflection around this diagonal line of the exponential function. Right? So there's two ways to graph a logarithmic function. The first is to just use a calculator, graph the function. The second would be to graph the exponential function and then reflect it. Let's do the first method. Okay? So let's plug in a graph. Okay? So we'll make our table. All right, now x has to be, remember our definition from way back over here, right? X must be greater than 0. So when I start plugging numbers into this, if I plug -1, -2, 0, any of those, they're not going to work because x has to be greater than 0. So let's start with 1. What power do I raise 3 to get 1? The answer is 0. Okay. Now any other number, I can plug 2 in, I can plug any number I want, 2 is going to be a decimal. Let's start with something that won't be a decimal. What power do I raise 3 to get 3? The answer is 1. Now I can do 4, 5, 6, 7, doesn't matter, all the way up to 9. All the other ones are going to give me a decimal. This would be 2. All the way up to 27 would be 3. See the pattern? All right, let's put this on the graph, and we'll use the blue for a logarithm. 1, 0. There's my first point. 3, 1. All the way, 4, 5, 6, 7, 8, 9. 9, 2. So my function is going to look like this. Just like this. The asymptote for the exponential function was the x-axis. It will never cross this. The asymptote for the exponential function is the y-axis. It'll never cross this. The logarithm will never be negative, no matter how far down you go. It will slowly keep going up, but it will never go pad down to the left of the axis. All right, and finally, remember that we can move these functions around. So if we start with the parent function, which is right here, we start with the parent function. If we look at A, that will be a stretch or compression, depending on if it's bigger than 0 or in between 0 and 1. It'll be a reflection if it's a negative. And then my translations are horizontal by h, vertical by k, which means that h is right here. So that means if it has a negative, if h has a negative, that means it goes to the right. If it's a positive, it goes to the left. K is right here. If k has a positive, it goes up. If k has a negative, it goes down. And this is just an example of all the different translations grouped together into one function.